In this video, we will try to construct the state space for a particular quantum system, or for photons, actually. So we start by considering a generic electromagnetic wave that you know that an electromagnetic wave associated an electric field that is described by this set of equations. So we are assuming that the wave is propagating along the z-axis. So the electric field of the wave along the z-axis is zero, because you know that if the wave is propagating along an axis, the electric field will be perpendicular to this axis, and the magnetic field will be perpendicular to the axis and to the electric field. So these are the equations that describe the propagation of the wave. We can rewrite, for example, Ax like that. So we can use a complex algebra. So it is, for example, take this part, like cos will be equal to yes. So we can rewrite Ax like this. So okay, and we can neglect the complex conjugate without loss of information. So also rewrite like this, because like rescaling the magnitude of the electric field doesn't change anything in the by the point of the physical view. Okay, so what we get is a new set of equations that we can write like this. The same for sorry. Okay. This is X equal to E0 times this guy. Okay, and Z equals to 0. So the components of the amplitude of the wave is E0 okay, and okay, where theta is actually a generic angle in the xy plane. So okay, so we have all the equations we need for describe the electromagnetic wave, the electric field associated with the electromagnetic wave. So now we will go further and consider the double slit experiment. So now I will take some time to draw. So we have a source of light. So we are considering the double slit experiment. Okay. This is a generic source of light. This is a generic plane with two slits. Okay, the slits have usually a diameter of like some nanometers, no, like probably 20, 30 nanometers or something. It's not important. Okay. And now the question is, imagine that on this side we have like we can collect the light that is passing through the slits and arriving here. So for example, let's consider this point. This is the y-axis. We ask, what is the intensity of light in this point? Okay, so the ray starts from the source, pass through the slits, and reach the point. Okay, and equal for this array. Okay, so the distance from each slit to the center is divided by 2 for simplicity reason. So and the length of this segment is L. We put our region here. So we ask what is the intensity of light here in this point. How can we solve this problem? You see that we have described the electromagnetic wave like this. So, for example, for the Ex, for X component of the electric field associated with the wave, you can notice now that before this line here, before this line, the 2 rays are generated in the same way and they follow the same path. So this part here doesn't count. So what actually counts, there is no phase shift here. What actually counts is the path of the ray after this first screen. So we have to make the assumption that the light is monochromatic. So we can, by saying that, we can write the intensity of the electric. We'll talk about the intensity later. Now, the electric field can be written as in a generic point on the y-axis. Okay. What is x1 and x2? X1 is the distance between the first slit, okay, and the generic point on the y-axis. From this equation, how can we derive an equation for the intensity? It's simple. Intensity in general is this guy. Okay, so okay, you can do the math and see that this is equal to 2 plus 2. We take the real part. Okay, so taking the real part, the result will be okay. So an important thing to notice is that in the generic in a generic point on the y-axis, we have two contributions. So this first term, as you can see, is the sum of the two contributions from S1 and S2 taken separately. And we have this term that is due to the interference between the ray passing through S1 and S2. So we can say this is an interference term. Now, the second, okay. Now we need an expression for x1 minus x2 because we want to calculate the intensity. Okay, so how we can get this expression is easy by some like geometric consideration on this picture. You will see that x1 squared is equal to rho plus and is equal to okay. If you think if you think a little about this picture, you will see that these equations are pretty obvious. So now this is equal, again, you can do the math by yourself, but you will see that this is equal to L okay, so we get this result. I didn't focus that much on like the algebra, but this you can check that this is true. So okay, we can substitute this in here. Okay, an important consideration is like that epsilon over L theta. So we get finally an expression for the intensity and for smaller angle theta. Okay, so we are considering small angles actually. So okay, what is cap? What is k? So k is actually 2 pi over lambda. Is like the I don't know how to say that in English, but this name probably is wave vector or something like that. Is a vector that has the same direction of the wave. So by substituting 2 pi over lambda, you will get something like this. Okay, so start a new page. In the final, we got okay. As you can see, this term will always be between -1 and 1. Okay, so we got 0. Okay, and in particular, you can see that we get the maximum intensity, okay, in theta equals 0. So at center, okay, we define the picture like this. So you get like actually you get theta equals to 0 at the center, okay. And yes, here we have constructive interference. But yeah, the question is, how can you explain this result? Like, how is possible that light plus light equals to dark? Okay, this is possible by assuming light as a wave, okay. Okay, so when you sum a top and a valley, you actually get 0. So now we need to define an important parameter, so the contrast. And is defined as follows. Imax is the maximum intensity, in this case is 4. As you can see, the maximum value for the contrast will be 1. Okay, so max contrast equals to 1. Okay, now we will move to photons, so we'll not consider waves anymore, but photons, and we will see what changes. So we have to make some assumptions. So like we know that is made out of photons, and as we can see from the picture here, okay, photons in the source are all created equally. So how is it possible that they end up on different zones of the screen? So because you know from an experiment from wait a second, it was Taylor, I guess, that's sending photons through the slits with a really feeble light. He has this experimental setup where he was able to actually send a really feeble light, and so really few photons per time. And in like on the screen, after 3 months of running this experiment, he actually got the classical, not the classical, but the interference picture that you get with waves. So something like this with, okay, principal maximum and secondary maximum, minimum, etc. So how can you explain that using photons? Change page. Okay. So we know that we say that photons are created by the same source in this experiment, so they are all created equally. So how can they end up on different zones on the screen? Okay. This is obviously in disagreement with like the classical determinism of the Newtonian mechanics. So if you get the same condition at the beginning, you should get the same results, right? But this seems in contradiction. So what we can say about that is that there is something that is not predictable in this process, or I would say random. And how can we describe randomness with math? Using probability. So in this process, there is something associated with probability. And how can we link probability to intensity of the light? Well, what is intensity? Intensity is the number, we can say that is the number of photons ending up on the point. So in some term, we can also say that the intensity at a generic point y is the probability of a photon to arrive at this point. So and this means proportional. Probability of a photon to end up in the point right. So now make a little resume. In the wave model, even a very feeble light produces the interference pattern. Okay, even if this light is really weak. But this is not what happens in experiment where the light became weaker and weaker. Instead of this, one start observing the emergence of quantum phenomena and the granular nature of light. Because at every emission, only a few points of the plate become illuminated, okay? And in an extreme setting, like when you can send a light that is so feeble that you are sure that there are really few photons passing through the slits. And at this point, it happens that on the screen only one point gets illuminated at a time. So like this, you have realized, like you can say that you have realized an emission of single photon. But if you keep this running for a long period of time, at the end you will collect the same interference pattern. Okay. So this means that you have, imagine a source. I will try to be more clear. Okay, you have a source of light. You can build an experimental setup to make sure that you send a light that is so feeble that you are sending, what is this? Okay, few photons at a time. Okay, you have two slits. Okay, a few photons at a time, and you have a screen. If you keep this running for months, you should expect that if photons are generated equally, these photons end up on the same point of the screen, like here or here, but not that they have a distribution like that. Okay, but if you keep this experiment running for months, for example, you will see something like that. Okay, this is the key point. Okay. Now we will introduce we will introduce this concept in the next video. So this is all for the moment.